Welcome to our Bucky weekend call of 12/7/8, December in 2024. And we're doing a fuller explanation. We're starting on page 49 in my book, the section A Limited Family, where we finish the discussion about polyhedra and move into a discussion of Euler's formula, which I don't know what that means, but it's going to be a fun time for my brain tonight. Anne, how are you feeling? And what are your expectations for today?
Glad to be here, and I planned it to come back in after I'm done with whatever I need to do for a bit, and then yeah, that's mainly the thing. And yeah, it's towards the end because this past months it has been normally very it gets a bit busy, so I it has affected my attendance in the meeting, so which I usually regret not being in, so I'm happy to be here today. So looking forward to this Euler's rule. Is it Euler's what? Law.
Yeah, Euler's formula. So we'll see
Formula.
what that.
Euler's formula. Looking forward to that. Okay. Yeah. And so Richard, how do you feel, and what would you like to take away today?
Well, I'm feeling blind, or at least I'm blind to you, but feeling good. I've last night and then tonight we've been to two festive dinners. One with my former Living Works company, and one with a group that I act as a treasurer for their organization. And so I'm full of joy and full of good food.
At least you're not sideways. At least you're not sideways.
No, that's right. I was sideways this morning on a trim tab session and I couldn't straighten out, but I'll be better this time. And if I have to go to the phone, I'm sure I'll be upright. Joe, how are you feeling, and what's your expectations for tonight?
I'm actually feeling pretty sick. So a little bit got the flu. But I'm on the upswing for sure. I'm feeling a little bit better than I did the other day for sure. So but life happens. I'm more concerned about the people around me, actually potentially my mother getting it. That's my big concern right now. So other than that, no, I'm just looking forward to going through this. We talked last week briefly. I thought we had an interesting conversation about some of the practical applications of Bucky's or of geometry in general, I should say. And I'm looking forward to jumping into Euler's law. Steve, how do you feel? What are you looking to take away from today?
I'm feeling pretty good. I'm looking forward to the math part. And so we're going to have this recording. So if you do miss it, Anne, it'll be here. But it's all about somehow I'm going to discover what Euler's formula has to do with the relationship idea and with polygons. So we're going to get going for it today. I've got to fix my phone and take it off of speakers. There we go. All righty. Here we go with the screen share. Well, I'll tell you. We go. All righty. So, Anne, we're getting started. Just as a kind of a review, we went through and discussed the idea of how polyhedrons seem to form, and they seem to be limited by space. How a hexagon's flat, how hexagons put together are flat, but how if you make a pentagon and you hook them together, they're not flat. So, and how they take this form, or how you put, if you put 5 triangles together, they're not flat. They take a form. Somehow space has a bearing on it. And we're going to learn all about that in terms of some kind of formula. So I'm very excited about it. So Anne, since you're here and since you're going to leave, do you want to read for a while before you leave?
Sure. So okay, it starts with a limited family.
Yes.
Okay. A quick review reveals a surprisingly limited inventory of 5 regular polyhedra, tetrahedron, octahedron, icosahedron, cube, and pentagonal dodecahedron.
Dodecahedron, right on. Pentagonal or pentagon, either one.
Right. Like it or not, we have reached the end. A child in kindergarten with the 2 rules carefully explained will discover the same 5 shapes. Space takes over, imposing the upper limit. This idea runs counter to the bias of our mathematical background that space is passive emptiness and we impose desired configurations. Invisible, unyielding constraints sound more like mysticism than science. If we dwell on this subject, that is because it is crucial to understanding the framework of Bucky's investigation. Space has specific characteristics, and we want not only to list and understand them, but also to begin to really feel their embracing qualities, a sense of structured space permeating all experience.
Okay.
Yes.
Let's see if it goes to the next page. Oh yeah, it's going to go to the next page because that's what we're doing.
Page 49, okay.
Okay, then it has pictures, evidently, of the 5 regular tetrahedra or polyhedra in review. There's your tetrahedron, the octahedron, the icosahedron, and then the cube, and then the dodecahedron.
Okay.
Okay, good.
Right. Okay.
And wrong way, Corrigan. I'll get this figured out.
I can read it from the book if you want.
Well, here it comes.
Okay.
I've just got to get here we go.
Okay. The regular polyhedra provide a good starting point from which to branch out in all directions. An 18th century mathematician, Leonard Euler, 1707 to 1783, greatly simplified our task with his realization that all patterns can be broken down into 3 elements: crossings, lines, and open areas. He thereby introduced the basic elements of structure, vertices, edges, and faces, which underlie all geometrical analysis. Bucky saw this contribution as a breakthrough of equal importance to the law of which Euler is known. For this precise identification of terms enabled Euler's other more famous observation. Euler's law. Euler's law states that the number of vertices plus the number of faces in every system, remember Fuller's...
My goodness. I'm
okay.
sorry, hang on a second.
Okay. Remember Fuller's definition.
Okay, there we go. Whoops.
Okay. Will always equal the number of edges plus 2. It may not sound like much at first until you reflect on the variety of structures from the tetrahedron to the aforementioned crocodile that all obey this simple statement. Okay, every system shares this fundamental relationship. The number of vertices.
Number of vertices can be precisely.
Okay, can be precisely determined by knowing the number of faces and edges and so on. Denote the number of vertices, faces, and edges by V, F, and E respectively. Then we have V plus F equals E plus 2. What about the constant 2? The other numbers might be extremely large or as small as 4, yet Euler's equation, the difference between the number of edges and the sum of the number of vertices and faces will always be exactly 2. It seems unlikely at first. To gain confidence in this principle, let's try it out on the regular polyhedra. Remember the 4 vertices and 4 faces of the tetrahedron? 4 plus 4 is 8, exactly 2 more than its 6 edges. Not bad so far. Similarly, we can count to check the other 4 regular polyhedra. The results are displayed in table 4-1.
Okay.
Right.
Vertices plus faces equals E plus 2. Edges. Edges plus 2.
So I won't read the table, yeah? The persistent 2 has led to some controversy. Fuller long ago assigned his own meaning to the recurring number 2 occurs. The recurring number 2 occurs in the equation to represent the poles of spinability. That requires some clarification. All systems, Fuller explained, can be spun about on a central axis. An axis has 2 poles, for example, north and south. And thus, at any given time, the 2 vertices must be poles. Subtract the 2 poles from the total number of vertices to get a number exactly equal to the combined number of edges and faces. Simply stated in Fuller's view, the permanent 2 represents 2 vertices, which as poles of spinability should be subtracted from the total number of vertices to equal the equation. It's a puzzling explanation.
Yeah, poles of spinability. So
spinability, not spinability. Got it.
Yeah, evidently these things spin.
Yeah. Yep. Okay, got it. But how does it spin on the cube though?
What's that?
The cube. Unless you put it on one of the one of the tips, right? Because the others, the pictures, the drawings for the others, they are in that position where you can see the axis, right? So the cube it can be in any what do you call any of the corners, right?
Well, I think what he's maybe getting at, this is new to me in terms of understanding the 2, is that it's like if you stuck a pole down through the middle of the cube and it was spinning around. The pole, of course, has a north part to it and a south part. So he's saying I think he's saying that pole that the cube spins around and the others is always 2, north and south. And
yeah,
that's why you add or subtract. Now,
yeah.
again,
Sorry.
Amy is saying that was a creative answer from Fuller. Whether he's right or not, I don't know, but it at least has some kind of rationale to it or some logic to it, that if something's spinning around, it's spinning on a north and south pole axis.
So this cube is spinning.
Yeah, so that means you have to turn it on its tip then, yeah? So
and you have to imagine a pole stuck down. I mean, that's what I'm doing. I'm trying to imagine a pole kind of stuck through the middle of in this case, the cubit, and so it can kind of spin around.
Yeah.
Okay, all right. Shall I carry on then?
I'm trying to really quickly. I don't know. Never mind. Go ahead.
Do you want to go, Joe? You want to say something first?
No, let's keep reading.
It'll it'll actually pull us away, I think, then from
Right,
what
so.
I was trying to think about. I was thinking in terms of another formula. But go ahead. Go ahead.
Okay. All right, I'll carry on then. Evaluation of significance is a tricky business, but we cannot avoid indulging in it altogether as Fuller's synergetics overflows with such speculation. It is ultimately puzzling that Fuller, with his emphatic observation that every polyhedron is a system, dividing universe into two parts, inside and outside, would not connect Euler's
Am I off the boat? Okay, here we go.
Euler's Euler's constant 2 with the implied 2 cells. His insistence that both parts of a system must be considered equally important provides a truly new orientation in geometry. At some point in any discussion about Euler and the polar 2, Fuller would speak of a structural system's inherent constant relative abundance. The meaning of the term eluded many. Fuller observes in synergetics that the number of faces in triangulated systems is always 2 times the number of vertices minus 2. The subtraction, he says, again, taking account of the 2 poles. He further states that the number of edges is 3 times the number of vertices less 2.
Does
Yeah.
that make sense to anybody?
So yeah, I mean, to me,
Well,
yeah,
we'll
sorry,
take
just saying the inside and
3.
outside is when
Take-
he's talking about that is
Well,
starting to get to one of the main points. And what I
just
think
try
that
it
there's
out.
also is revealing some patterns as well. And these patterns you can kind of start to see is that the idea of 2 and the relationship between the 2. So if you have a North Pole and a South, you can start to see that there's inherent patterns in nature itself. And then and then I almost look at this in terms of what really kind of came to me is almost like a dialectic. And I start to think of something, even unity is plural minimum 2. This is where this starts to come into what I'm starting to think about, when you can start to see the importance of this, of being able to see this patterns between the 2 poles. And there's an integrity to those patterns.
Well,
so
now try it.
I'm sorry, Richard.
Well, take a tetrahedron. He
Yeah.
says that the number of edges, which is 6, is 3 times the number of vertices less 2. There's 4 vertices, minus 2 is 2, times 3 is 6.
Right.
And you could try it out on the others too, but for me, for the tetrahedron, is a good example to work it backwards like that. To
Correct.
say
So
4 minus 2 times 3 equals the number of edges. So 6 equals 6.
Well, you're getting way more out of it than I am. Can you guys hear me?
Yeah.
and
The only one is
I don't know.
I can't make sense of the last one though, the pentagonal dodecahedron. If you take 30, 20 minus is 3 times the vertices, right? So that's the only one. The rest actually fits exactly as he says it, except for the last one. I don't know how to calculate that. 30, and because 18 is not 3 times, 30 is not 3 times of 18 though.
Does anybody understand what Ann just said?
No. Could you ask that again?
Let's
I'm
try
sorry.
it, and
Okay, if you see icosahedron, right? it's 30. 30 is 3 times 12 minus 2, which is 10. 30 is not 3 times of 20 minus 2, which is 18. So that's the only one that doesn't. The rest all fit exactly as he said it, except for the pentagonal dodecahedron. Yeah.
30.
Number of edges, 6, yeah, 12, 30. Yeah, that's interesting.
Yeah. Because 30 is definitely 3 times 10,
Yeah,
3 times of 10, but only the last one. Maybe I don't know whether he'll have an explanation. I'll have to run out and I'll be back the minute I can.
Yeah.
Okay.
Cool.
I'm gonna leave
Well-
this running. Huh?
All right, we'll miss you, but you'll come back when
Yeah.
you come back, and blessings to you and your granddaughter.
Thank you.
Yeah, yeah, absolutely.
Okay, I'm keeping this.
Good. Now, look, I noticed that the octahedron and the cube have the same total, and the icosahedron and the pentagonal dodecahedron have the same total. Isn't it interesting that I didn't add these colors? Are they that way in the book? Because yeah, they're that way in the book. They're grayed out in the book. So the octahedron and the cube just switch numbers. And the icosahedron and the pentagonal dodecahedron switch numbers. The faces, the the vertices plus the face is equal to the face plus the vertices. I mean, they're the same values, which is very interesting. Pardon me for sneezing.
maybe we should double check that. Who knows? Maybe there's a typo.
I know that symmetry is even highlighted.
Yeah,
Well,
So
and when you see what Anne was saying, that if you take vertices 20 minus 2, and that's 18 times 3, you don't get 30. Whereas the others, if you minus 2 times 3, you'll get the edges. 6 minus 2 is 4 times 3 is 12. 8 minus 2 is 6 times 3. There's something wrong there too in the cube.
you mean of Anne's derivation?
No, yeah, but Anne spotted the dodecahedron saying 20 minus 2 is 18 times 3 is not 30. And now I'm just looking at the cube and saying, well, 8 minus 2 is 6 times 3 is not 12.
Well, that's
So
not
then
Euler's
on the
formula.
octahedron, 6 minus 2 is 4 times 3 equals 12. On the tetrahedron, 4 minus 2
But
times
that's not
3 is
Euler's.
6.
But
yeah,
that's not Euler's formula. If you're going to use algebra, you'd have to take the v plus f in parentheses and subtract 2. In other words, E equals v plus 2 in parentheses minus 2. In other words, you have to add the v plus the f before you subtract the 2. You can't just subtract the 2 from one of them. You
Well,
have
that isn't what the text says. So go down to the text a little bit further and let's follow what the text says.
What does the text say? Well, you know what dawns on me? It doesn't matter if you have v plus f in parentheses minus 2, that means that you could take v minus 2 plus f, or you should be able to take v plus f minus 2, and you
Right.
should have the same thing, right? Because they're all addition. There's no,
right.
it's totally a mathematical relationship. It's not arithmetical, or it's not
But go down to
algebraic.
the text.
Okay,
And right
which
now,
paragraph?
well, just down the bottom of the page there.
There is another way to view the constant element, as you may have guessed. What are the characteristics of the variables included in Euler's laws? Zero-dimensional points one-dimensional lines and two-dimensional areas. Well, that's cute. I didn't understand that before until I just saw that. Each a level higher than the last. The law compares all aspects of structure almost. Something's missing. Three-dimensional space is the next and the only absent parameter, and its geometrical units corresponding to vertices, edges, and faces are cells. Why are cells left out of this fundamental relationship? The other view, as expanded by Loeb, says they're not. Oh my gosh.
No, let's keep reading on that. 'Cause-
It's what?
well, let's say let's read down to that paragraph because they've added plus C, meaning the cells, rather than plus 2.
Okay. Who wants to read down?
I can read though. Recall Bucky's definition of a system as subdivision of space, creating an inside and outside, both equally important two cells. Could the constant 2 in the equation be incorporating the otherwise only missing dimension? Indeed, it is. Euler's law is actually a special case of Scaphole's formula for any number of cells. In other words, if the number of cells C is substituted for 2, the equation holds true for multicellular structures. That is, arrangements with more than 2 cells, V plus F equals E plus C, even when C is greater than 2. Evaluation of significance is a tricky business, but we cannot avoid indulging in it altogether. A fuller synergetics overflows with such speculation. It is ultimately puzzling that Fuller, with his emphatic observation that every polyhedron is a system dividing. I need you, Steve.
His emphatic observation.
Yeah. And I need you to scroll down.
You can't see it on the screen.
Oh,
I
I'm
can't
sorry.
see.
I'm falling out of the book. I'm really sorry.
Yeah.
I'm so sorry. Thank you.
No worries. In fact, the observation of that every polyhedron is a system dividing universe into 2 parts, inside and outside, would not connect Euler's constant 2 with the implied 2 cells. His insistence that both parts of a system must be considered equally important provides a truly new orientation in geometry. At some point in any discussion about Euler and the polar 2, Fuller would speak of structural systems' inherent constant relative abundance. The meaning of the term eluded many. Fuller observes in synergetics that the number of faces in triangulated systems is always 2 times the number of vertices minus 2 with the subtraction, he says, again, taking into account 2 poles. He further states that the number of edges is 3 times the number of vertices less 2.
Yeah, that's the text right there that if we take it back to the formula table, we're saying that it works with the tetrahedron and the octahedron, but it doesn't seem to work for the cube or the pentagonal, the dodecahedron. That's why I was saying go down to the text and let's see if we can follow the text and then substitute the numbers and see whether it works for all of those 5 up there.
Which text do you want to go to? What
But
what's the
just that last sentence that Joe read down further.
okay?
You got to go down further again. Let's go further. There, right, that last sentence. Number of edges in a tetrahedron is 6, and it's always 3 times the number of vertices, which is 4, minus 2 is 2 times 3 is 6, so it works. So let's try that on the cube. So
Okay.
up there it says,
You want to go back to the table then?
yeah. So what we just need to do is hold that statement of 3 times the number of vertices less 2. So yeah, okay. So now we see that on the tetrahedron, E is 6, and supposedly if you take 4 minus 2 is 2, and times 3, you should get 6, which you do. And on the octahedron, you should be able to take 6 minus 2 is 4, multiply by 3, you should get 12.
There it is.
And on the cube, if you take 8 minus 2, which is 6 times 3, you should be getting to 18, which you don't. On the icosahedron, you should take 12 minus 2 is 10 times 3 is 30, you get 30. And then, and Anne spotted it, this one, of saying 20 minus 2 is 18 times 3 is not 30. So somehow or another, it's not working for cubes and the dodecahedron.
And I wonder if it's this shaded area is actually indicating that. Because notice that the 8s are shaded and the 20s are shaded. I have no idea why they're shaded. Do you know why they're shaded?
No, and if you did what you were talking about of saying you've got to add, I think you were saying you have to add the V's and the F's, like they're in brackets. So you got 6 plus 8 is 14 in the octahedron, minus 2
Is
is
12.
12.
That should be the formula for, in other words, E equals V plus F
Yeah.
minus 2.
So there we're, so let's take the other one, the tetrahedron. 4 plus 4 is 8, minus 2 is 6. Let's
Right.
take cube now. Is 8 plus 6 is 14, minus 2 is 12.
Yeah.
Let's take the next one. 20 plus 12 is 32,
2
minus
2 is
2
3.
is 30. And the other one, of course, is the same number, so it's going to be 30. So that's kind of interesting. So you're saying that the V and the faces, vertices and the faces added together minus 2 equals the edges. And we
Right.
tried it and it works.
Oh, okay.
Yeah. Well,
Whereas
that's
we tried
All
what
right.
that bottom sentence says, it works for 3 out of the 5 and not 2. It's not, doesn't work for 2 of them.
the bottom sentence says that.
Well, yeah, look, it says that, let's go down, because that's what we were trying. We were trying to make the bottom sentence work, and it worked for 3 out of 5. Just go down further.
2 represents 2 vertices.
Oops, sorry.
Whoop. Amazing. Got that sentence there. Where'd it go?
For some reason,
He further states that the number of edges is 3 times the number of vertices less
less
2.
2.
And so in a tetrahedron, that's easy. You can take 6, or you can take 4 minus 2 is 2 times 3 equals 6. And it works for a couple of the others, but it doesn't work for 2 of them. But when we did what you said, added the vertices and the faces, and minus 2, you get the number of edges on every one of them. Interesting.
Well, all I did was do simple algebra. I just
Yeah,
took that, I
exactly.
just took it. I'm not understanding the value of this conversation at all, other than Euler and Fuller are musing over the over the arithmetic relationship between the vertices, faces, and edges. And as you're pointing out, however, something that's written in this book, the statement, he further states that the number of edges is 3 times the number of vertices less 2. That seems to work. But there was that one thing that didn't seem to work, right?
Well, I mean, isn't
There
the
was
whole
two.
it can,
2 didn't work.
well, I mean, the whole point is that in the one paragraph, the 0-dimensional points, the 1-dimensional lines, the 2-dimensional areas.
Which I thought was pretty interesting here.
Yeah,
Zero-dimensional points, one-dimensional lines, and 2-dimensional areas. And then she goes off to mention cubes as cells, which I didn't understand either.
well, but then it says the law compares the aspects of the structures almost.
No, what she's
not- and
getting
she
out
says-
about cells,
Well, wait a
she's
minute.
saying
Don't-
cell
Richard, please.
substitutes for 2.
Then she says something's missing. 3-dimensional space is the next and only absent parameter. Its geometrical units corresponding to vertices, edges, faces are cells. Why are the cells left out of the fundamental relationship? The other view is expanded on by Lubes. Says they're not. And so
Now keep reading and you'll see that the cells then are 2.
right, but then even if that is true,
And then
Yeah.
further on, they're saying that doesn't matter what number of cells you have beyond 2, it's going to work out. So we'd have to try some calculations to see whether that's true.
I have another point that I want to bring up, but I don't want to take us off on a branch until we're ready to do that. Now she's bringing up Euler's law is actually a special case of Schläfli's formula for any number of cells. In other words, if the number of cells C is substituted for 2, the equation holds true for multicellular structures, that is, arrangements with more than 2 cells.
Yeah.
I don't know what a cell is. What's a cell?
Well, I mean, in the basics that she's going at now, instead of saying that 2 is the poles or 2 is something else, the 2 are 2 cells. Loeb is claiming that there are minimum 2 cells, I guess. And then if you know of a structure, if you know how many cells are in a structure, whatever number of cells there are, you can work it back and you'll find out how many vertices, how many faces, how many edges.
Well, see this, though, as soon as you say that, I want to leave this conversation and focus on something that maybe challenges your historical referencing to Bucky's definition of a system. She says that Bucky's definition of a system is a subdivision of space creating an inside and an outside. And there's your an inside and an outside. So that's where the tetrahedron is the minimum structure, because there are opposite sides in a triangle, but there is not an inside and an outside.
Right.
And evidently, inside is one cell and outside is the other cell. Is that what you're reading, Richard?
Well, I mean, it seems that they're going through a number of possibilities of what is this 2.
right.
And
What is
it
it?
started out with, it's almost just like an arbitrary 2. Then Fuller seemed to have said, no, it's the polar 2. And then there was another one. And then Loeb is coming along as his mathematical background, saying, no, it's cellular too. And this, so you substitute the 2 for a C, and then if you know see, what you're going to have to do is you have to know the number of cells, I think, and you'll have to know one of the V, F, and E. And when you put that together, you should be able to determine the rest of the V, F, and E.
Yeah, but what is a
Right.
cell? I see an inside and an outside are the 2 cells.
Yeah, well, that's the point he's making. If this is the way to
This is the idea of like a self.
acknowledge 2 things. The inside, outside are an inside cell and an outside cell too.
The
Well,
self and
except you-
other.
What's
Just
that,
like-
Joe?
No, I mean, this is, yeah, it's the relationship between, this is why you start to be able to look at the relationship between the 2 points.
Well, except
Yeah,
my
but not
confusion
yet.
lies, if a cell is divided, if the cell is based on the definition of a system, a subdivision of space creating an inside and an outside, then the tetrahedron, the cube, the dodecahedron, I think all of the solids that we're talking about so far only have 2 cells. There's an inside and an outside. Or am I missing something?
Well, but we can continue with that notion of starting at that minimum 2.
Right.
There's an inside cell and an outside cell. And looking at it in terms of that way, instead of looking at it from what Fuller started out with, and that was the polar 2, north and south. I think Loeb is now was saying that, no, I don't think that's right. But I think inside, outside, giving you cell in and cell out is 2. So I think it's cells. And then this Scheffler guy, somehow or another, he's worked it out. It doesn't matter how many cells there are, the formula still works. But we'd have to go and look at his work, I guess.
Well, I don't understand what a cell is and how a cell relates to a tetrahedron and a dodecahedron in some fashion. I don't
Well,
understand that at all.
you just described it in the sense of inside and outside.
Well,
And
tell me,
they're being called cells.
and so in other words, there are 2 cells in a tetrahedron, there are 2 cells in a dodecahedron, inside and outside.
That's what we are sort of depicting now. We'll find out whether or not we're onto it correctly, but yeah, that's how I would see it, inside and outside, for all of them.
And how does that relate to Buckminster Fuller's polar 2 idea?
Well, I think it's being put aside.
Well, it says right here, at some point in any discussion about Euler and the polar 2, Fuller would speak to a structural system inherent constant relative abundance. Whew, my brain is blown away.
Well, she's put polar 2 in quotations, so I don't know if that's sort of like a placeholder saying, well, okay, well, let's not throw Fuller's idea of the polar 2 out yet, but however he wants to talk about it, he would be talking about a structural system inherent. It's inherent constant relative abundance. And again, I'm not sure what constant relative abundance is, but it could be that we're back to the other formula or the expression that says a whole is not one. No, unity is not one. It's plural, minimum
of
2.
2, because there's inside and outside.
And
well, here's something. Fuller observes in synergetics the number of faces in the triangle systems is always 2 times the number of vertices minus 2. That conversation right there is exactly the discrepancy you pointed out that we pointed out in this table back here. Because what you pointed out was, oh no, you didn't point that out. Let me go back to the table though. That the formula as it's presented works for the cube, but not for the octahedron, works for the icosahedron, but not the pentagonal dodecahedron. In other words, the formula works off the vertices. It doesn't work off the faces.
Right.
And when,
That's
Yeah.
the difference. Yeah, that's,
but as you pointed out, the octahedron and the cube, that's where that shaded area comes in. Golly, I'm just totally
But,
confused.
Actually, you can
when
feel it.
you said, in terms of simple math, that you take the vertices and the faces, add them together and subtract 2, you get the number of edges for everybody.
Yeah.
But that isn't what the text is saying. So it's like, so, and if we go back to that last one that you were just looking at about Fuller, and because it's a slightly different wording from the one that we were working with a minute ago. Where did it go there? Just below there. So he says, always 2 times the number of vertices. So going back to the tetrahedron, 4 vertices, so 2 times 4 is 8, minus 2 equals the number of edges. Now, we could try this formula on all the others and see what happens.
I'm gonna do a little bit of a trick here, because I keep wanting to look back at that table. So what I'm
Yeah.
gonna do is I'm gonna grab the table and I'm going to
Put it down there.
I'm gonna put it in a, wow, I'm noticing my wow. Here we go. Here we go. I'm gonna grab this and put it in a window through a snippet window, and that way we can just refer to it anytime we want to. So there's your snippet window. Bam. Now that's the snippet window. And then, come on. What the heck? Oh, that's weird. Yeah, okay, I got rid of that, but hang on, I want to bring it up again. So now we're going to go down to here. There we go. Now I can bring this back anytime we want to. For some reason, I'm not able to drag it around on the screen. That's so weird because, oh, there we go. There, now it's dragging around.
I
Okay,
can't see it.
so now we can put it there and then we can look at any word we want to. What words do we want to look at?
I can't see it at all.
Well, I know, I just flipped it off. This allows us to look at this bottom paragraph.
Yeah, go down a little further.
Okay, I'm going to go down a little further, then I'll bring it back when we
Yeah,
get there.
now stop right there.
Yeah, hang on. Okay, good. And then I brought back the table. Okay, good. Is this
So,
helpful?
well, let's just work it. Always 2 times the number of vertices. So give me the number of vertices in a octahedron.
6.
6. So 6 minus 2, or no,
Times.
yeah, 6 minus 2 is 4, times 2 is 8. How many edges in a cube?
It says there are 12.
Yeah, that's standard.
But if you take 8 minus 2, that's 6 plus 6 is 12. I'm sorry, I'm off the point. I don't want to distract, but suddenly I'm getting something here where it says the reason why we're subtracting 2, Fuller says, is because we're taking into account the two poles.
Right. So he's
So
back
that's-
to subtraction instead of addition.
Yeah. But he subtracts the two only off the vertices. But as you point out, that works for the octahedron, but it doesn't work for the cube, and it works for the icosahedron, but it doesn't work for the pentagonal dodecahedron.
Right.
I think there's something here that every one of us are getting something that doesn't make sense, but we're not exactly each of us focusing on the same thing that doesn't make sense. Maybe if we continue to read, this will all resolve. Does somebody want to read again, review anything with this chart before we continue? What? Go ahead.
Yeah, I mean, we could keep going to see, again, this is my assumption that what we're working through right now is some kind of basic balancing of numbers. But eventually we're going to get to that other formula that really tells us how we get the, with a given number of n's, we can figure out how many interconnections there are between them, minimum, or how many relationships are between them. And that to me is the functional applicable formula. That this one has never made any particular sense to me, other than what we're trying to do now is to get it into our heads that yes, it works. Yet as we're trying it now, it works for 3 but not 2.
Which boggles my mind.
Yeah. And then we've got Fuller saying, well, no, I use I minus 2 because of the polar 2, and somebody else is saying, no, you add 2 because of just a constant 2. And then now we got Loeb saying, no, you add 2 because you got 2 cells. So,
and it's not consistent with the octahedron to the cube and the icosahedron. I mean, the cube
yeah,
and pentagonal dodecahedron do the formula, anything applied to vertices from Fuller is not working on those two things.
yeah, it seems that way. Unless it's to say, unless the 3 of us are so dense that we can't read what it's really supposed to be telling us.
Yeah, maybe you're saying that my ignorance is contributing to the confusion. I hear that's what you're saying.
No, I think it's like there's
No, I know I took it personally.
there's 3 simultaneous ignorances.
Okay, well, here's our next reading. Maybe we should continue with this and see if it makes any helps
Yeah.
pull. Okay, who wants to read it? I'm stepping away for a minute, but I'm listening.
I'll read it then. It's
Okay.
turning these two statements into simple equations, we have F equals 2 times V minus 2. And we have E edges equals 3 times V minus 2. And now he's working with faces and edges. And then simplifying, we've got faces equals 2V minus 4. And E equals 3V minus 6. And we have F plus 4 equals 2V. E plus 6 equals 3V. Combining the two equations by subtraction, we have E plus 6 equals 3V minus F plus 4 equals 2V.
Mm-hmm.
And so we end up with E minus F plus 2 equals V. And we should take all those numbers and test them in those formulas.
Okay, I'm back. Did anything resolve?
No, other than we could test them out. So if we take faces, 4 faces, I'm going to go back to the tetrahedron. 4 faces equals 2 times 4 minus 2 is 2. So 2 times 2 equals 4. So that works. Or if I use the E equals, I get 6 in the tetrahedron should equal 3, 4 minus 2. So it should be 3 times 2. That works. And then you simplify, he said, take the 4 faces minus 2 times 4 is 8. 2 times 4 is 8 minus 4 is 4. So that's the number of faces. You do it, E equals 3V minus 6. You get 6 should equal 3 times 4 is 12 minus 6 is 6. That works. Faces plus 4 should equal 2 vertices. So faces plus 4 is 8, and 2 times 4 is 8. 6 plus 6 is 12, should equal 3 times vertices, so 3 times 4 is 12. Combining the two, we end up with E minus F, so that's 6 minus 4. 6 minus 2 plus 2 is 4, and that's the number of vertices in a tetrahedron. Or 6 plus 2 is 8 equals 4 plus 4 equals 8. And I guess, I guess what we probably should do then is go to the two that didn't seem to work out up above and test them on these formulas and see what we get. So can somebody help with the cube now? So the cube has how many faces?
The cube has 6 faces.
Okay, so we got 6 should equal 2 times the number of the vertices is 8.
Yes.
Well, that's 8 minus 2 is 6 times 2 is 12. That's not the number of faces. So let's try those numbers again. How many faces in the cube?
6.
There's 6 faces, 8 vertices.
Oh, 8 vertices. Let's see again, 8 minus 2 is 6 times 2 is 12.
Correct.
And that doesn't equal the number of faces. Let's try the other one. How many edges in a cube?
12.
12. Okay, so, and the vertices is 8, is it? See, so it's going to be 3 times 6 is 18. That doesn't equal 12. Oops. Maybe we have to try one of the others that worked.
This reminds me of my days in philosophy. It didn't work. It didn't work for me.
Well, I think
And I
when
have
we look ahead,
two
there's actually
geniuses here to help me.
there's
What, Joe?
some explanations as to think that maybe going ahead and reading a little bit more maybe bring some clarity too.
Well, there should be clear clarity in making this thing work. All those,
Right.
and to go back and test it
And I
against
think the
those 5.
explanation is to maybe as to what what isn't working for us and what is working will be revealed.
Well, it's not, to me, it's not a question of what's working for you and me or us.
No, no,
It's-
no, no.
It's what's the formulas doing or not doing when you apply it.
Correct. The explanation of the formulas themselves.
And so far, there's no explanation why those values in that chart are highlighted.
Well, and I don't know, could be, well, I don't know. I was just gonna say, just highlighting, one's faces and one's edges, but or vertices. Let's go back up to the table and somebody stay on these formulas because it worked with a tetrahedron. So maybe if we look back at, we'll see what we've inserted incorrectly or something, maybe. I don't know whether. So we're on the edge of saying we either are making mistakes or we're going to blame the book or we're going to blame
And the book can't.
Euler, or we're going to blame Fuller, or going to blame Amy for not making it clear. Even.
So where do you want to go from here? I'm happy to do it. We can continue to
Well,
read.
I was gonna go back up to the table just one more time.
Okay, there's the table.
If somebody can stay with these formulas and give
Yes.
me the numbers, or I'll give you the numbers off the table and
Oh,
you apply them in the formulas and let's see what happens. You guys do the math.
I'd been flopping back and forth between the content and the table, and I realized I wasn't sharing my screen. I was sharing just the book. So here I was flopping back and forth, and you guys never saw it. I was seeing it, but you guys weren't.
Yeah.
Okay, there's the table.
We go back to try the octahedron again. We've had there's pick one of those formulas. Oh, wait a minute here. Okay. One of those simple formulas. Let's take F equals 2V minus 2. Let's go back up to that.
-2 or -4? Because F equals 2V minus 4, it says.
Well, there it does, but let's
Oh.
go try that one.
Okay, I can put this here. Oh, I can pull the tab up here, and I can put it down below so that we
Okay.
can that formula.
So F is 2V minus 2. So F is
You have to go V minus 2.
eight faces, and it's V is 6 minus 2 is 4.
Times 2.
4 times 2 is 8. That works. On the octahedron. Let me try it on the cube right now.
It's
So
not going to work.
the cube has 6 faces. It says, right?
Mhm.
And vertices. So 8 minus 2 is 6 times 2 is 12. So you get the 12, but you don't get the 6. 2, the vertices are 6, or no, 8. 8 minus 2 is 6. 2 times 6 is 12. But the faces are only 6. So, yeah, this is about the time I'd be walking out of the class saying, I give up. I don't understand.
Well, I've been listening to you, hoping that something would come through, but we have exactly the same problem occurring with the cube and appendage.
Well, let's try again. Let's try the icosahedron. So we got 20 faces, and we've got 12 minus 2 is 6 times, no. Yeah, 12 minus 2 is 10, times 2 is 20 faces. So it works. And then the next one, we've got 12 faces, and we've got
20.
20 minus
Vertices.
2 is 18, times 2 is 36. So that doesn't work. Just like it didn't work before.
Yeah. Well, the next time you see Amy,
Yeah.
you can tell her we have a bone to pick. Tell her we just missed the boat. That we're missing a trim tab here somewhere.
Somewhere, yeah.
Wow.
But what it's done though for me is that whenever we finish, like say this evening, it now, you know, pushes me to go back to those pages in the book and, you know, get pen and pencil out again and keep trying to work through all those different formulas, which I probably have never done before in terms of sometimes your eyes just glass over formulas instead of really testing them out, which is what we're doing. You know, this thing with Amy, it could be that we get to a place where we're clear in our own mind about what's not working, and we send a communication to her to say, help us.
Well, she definitely wouldn't reply to me, but she might reply to you, Richard.
Yeah, well, I don't know. I mean, she doesn't know me from Adam, other than I could tell her that I sat in your class in, you know, 95. That might be enough to say, oh, I didn't
Yeah.
I didn't think anybody would ever remember that class.
Well, what should we do? Should we start reading about duality?
Yeah, well, let's keep going because we're eventually going to get to this other formula, I think. The one that I know I like, and more of us are getting to like it in terms of being able to determine the minimum number of relationships between a given number of nodes.
Well, I like that formula, Richard, because it works.
Yeah,
And I have not seen that. I'm not getting the same results here.
yeah, me too.
Kind of weird. So, Joe, do you want to read, or Richard? Who wants to read?
Well, I'll read. This is to start with duality.
Sure. If that's where you want to start.
Yeah.
All right.
So duality, table 4.1 reveals a curious pattern. Notice the relationship between cube and octahedron. Now we have been.
Yeah.
Along with the similar pairing of pentagonal dodecahedron and icosahedron.
Okay. She's addressing our problem.
Yeah. Polyhedra, thus related each with the same number of vertices as the other has faces, are called each other's dual.
Aha.
We are therefore introduced to duality as a numerical relationship. The vertex and the face tallies are simply switched. There's your gray too, maybe.
Yeah.
Reassuringly, the significant extends. Loeb observes the geometric manifestation of duality in precise matching of vertex to face. The two dual polyhedra line up with every corner of each meeting, the center of a window of the other, as the correspondence implies. Figure 4.7a shows the dual relationship of the cube and the octahedron.
So they don't add up because they're duals.
And she also defines up there constant abundance or constant relative abundance as well.
Well, I learned about duals in the last
Previous.
couple of weeks from Wednesday's meeting. That you take a dual is created by taking the center of each face and drawing a line to the center of the object. So the dual of a tetrahedron is a tetrahedron, but the dual, I can get on Zoom here, or I may get on Google, and we can do what is a dual of what is the dual of an octahedron? It's a cube. The dual, I saw the design right here. See, there's the
Mhm.
center point in the center of each face. That's the dual. What is the dual of a pentagonal dodecahedron? The dual of a pentagonal dodecahedron is a regular icosahedron. Well, of course it is. That's what she just said. She just said that the icosahedron is a dual of the pentagonal dodecahedron. That's why
Yeah,
those gray.
and the
Or
other thing is that when we added them together, and followed the formula, they all work.
right. Well, she's discussing this phenomena here, but she hasn't justified it mathematically with her formulas at this juncture.
Well, I guess maybe that means we have to keep reading.
All right, maybe it's an invitation to keep reading. Okay, good. Here comes the next page. Go ahead, Richard.
So we have conspicuously ignored one member of Plato's polyhedral family. What is the tetrahedron's dual? Following Loeb's example, we count elements to predict the answer and find the same number of vertices as faces, right? Therefore, by interchanging the two elements to find the tetrahedron's dual, we generate another tetrahedron, figure 417b. Once again, the minimum system stands out. Only the tetrahedron is its own dual. Put the two of them together. Whoops.
You just,
Oh, yeah, there they are. Put the two of them together to check the four windows and corners line up, and curiously, the combined 8 vertices of two same-size tetrahedra outline the corners of a cube, as Fuller never tired of explaining. Two equal tetrahedron, positive and negative, joined at their comfort centers, common centers, define the cube.
Which is interesting because the octahedron is the symbol used by the Kabbalah and
Yeah.
several other traditions, including maybe Native American, as the 7 directions which define three-dimensional space. I hope that didn't confuse anybody.
They're using which again?
And in Kabbalic in mystical Kabbalah and Native American and other Aborigine type spirituality or geometry, the octahedron is the shape that defines the 7 directions. You have the up and the down, the north, south, east, and west, and the center. That's the 7 directions. And evidently,
4, 5, 6.
that
Oh, I
dual
see.
is a cube.
Right.
And therefore, we have 3D space.
oh,
See, now that's a revelation to me.
yeah, that
And
was,
then though, when you this is back to the squaring and so forth. When you look at the cube, it takes up way more space
yeah,
and numbers to get the same volume as a tetrahedron. Or in the mathematical, when you when you use squaring, like a square and a cube and everything, it takes a lot more work to get the same answer that triangling gets you with less space or less area taken up. And
Right. This is-
that's where Fuller used to say, um, man and nature both get the same answer. Whoops, just hang on.
Yeah, I think actually, just looking at this now, that was actually a revelation that when you just drew it like that.
about the
With the- yeah,
octahedron, the
exactly.
7 directions of the octahedron, how they create three-dimensional space.
Yeah, exactly.
What I'm not understanding is how the dual, I wish Richard were here. I might have to
Yeah.
repeat. Oh, do it. Richard's back.
Yeah,
We're just musing about how the octahedron create this are the 7 directions of a cube, three-dimensional space, and at least in Western eyes. And I was just going to remark that while the dual of a tetrahedron is a dual tetrahedron, if you expand the dual, it becomes a Merkaba, which is the double tetrahedron, which is like an amazing thing.
right.
And I guess no other what we might call Platonic solid, even though from a Bucky point of view, we're going to argue that none of these structures are solids. So we'll say structures. That's unique about the tetrahedral structure is that it is its own dual, and therefore at some way creates this Merkaba, or
Yeah.
the double tetrahedron, which is represented in a 2-dimensional Star of David, by the way.
Yeah, 2-dimensional Star of David. Yes, yes, yes.
Yeah,
But as you're saying, you take that dual triangle or a tetrahedron in that picture,
yeah,
you say pull it
yeah,
outside of those other 4 faces,
yeah.
and you get the um, what
Double tetrahedron or the Merkaba.
the Merkaba, yeah, and this is what you see, right?
Exactly.
Right.
And this is what's so fascinating for people as you say, in sacred geometry, to see it come out like that.
Yeah.
Yeah, and it's just the duality of the tetrahedron. Yeah, wow.
Hmm. Positive, negative.
Very interesting.
Feminine, masculine.
This is kind of interesting here. Here is the Merkaba or the tetrahedron inside of the tetrahedron slowly growing until the edges meet, and at that point they become the Merkaba.
Hmm.
Yeah,
So this is called a compound tetrahedron. This is called a tetrahedron 2 compound, and this is called a 2 tetrahedra compound. Interesting.
Can you put that in the chat?
This page or this
Yeah.
picture?
Either one. The page would be sufficient.
And notice this is from Stephen Wolfram, you guys.
Hmm.
Because, and it looks to me like this shape right here, this,
That looks
well,
like
of course,
the
this is a
amplitude.
truncated double tetrahedron that's not regular because it's lopsided and then it's truncated.
right.
Let's see if I can make that into a whole page. I just flipped on it, Wolfram Math. Yeah, there it is right there.
Can you put that? Yeah, just put that page in the chat.
Okay. There we go. And Wolfram, I'll tell you, he's the next dude because his whole concept of computational irreducibility and the idea he explains the second law of thermodynamics, entropy. He explains entropy as simply a phenomenon of computation of a computational universe. That the reason why entropy doesn't go backwards is because the universe is computing. It's creating itself, and it can't go backwards. It has to go forward.
Mm.
So, anything else we want to examine here? Yeah, that's not the same thing. This guy here is interesting to me. This is the 2 compound. I want to know why it's not. I guess I have to take this out first of all. Then I click on that. There we go. Again, this is Stephen Wolfram. Whoops. I guess this takes us to the same page and we'll find these below. Boy, now he starts to combine spherical space into, wow. Oh, look at this one. He's got 4 tetrahedra together.
Oh, yeah.
Whoa.
Huh.
Well, that's an interesting exploration. Does anybody, what should we do next here, guys? Is there anything you want to reread or shall we just plow ahead?
I mean, I think, did we miss a paragraph up at the top?
Now, here's what boggles me here. It says 2, this is from Bucky, 2 equal tetrahedra, positive and negative, joined at their common centers, define the cube. We're not seeing that here. And it says also see 4-7C. Okay, there's 4-7, and here is C down here. Well, this is the famous, oh, yeah, because a cube exists outside of this. Let me see if we can do this. I'm going to go back over to here and I'm going to say compound tetrahedra as a cube shape. When you overlap 2 regular tetrahedra in a specific way, the edges of the combined shape form the diagonals of the faces of a cube. Now, we're not seeing this. Let me see if I click on images, if it just becomes obvious, because I have an obvious image like this in my, there it is right there, guys. And here it is right here. So this is your Merkaba sideways, and it's forming a cube.
Mm-hmm.
So a double Merkaba forms a cube, and the octahedron creates a cube.
Right.
Okay, well, that was my
And I really like this, the dual decahedron or tetrahedron coming out of it's insideness, if you want,
yeah,
and then join all the points and you got a cube.
exactly. That's kind of an interesting puppy. If I open this up in a new window, I can show you, this will be this link, Joe. And it'll give you that graphic, right? Oh, geez, look at that.
Mm.
This is a dodecahedron with 5 tetrahedra. I had no desire to do this to myself. I'm not going to be able to sleep tonight.
Mm.
Holy mackerel. Andy.
That's actually interesting right there.
Well, there's your cube. Whoa, why didn't he just show me this one? Why did he have to do this? This is a dodeca. This one up here is a dodecahedra
Yeah.
with 10 tetrahedra. And this one here is a dodecahedron with 5 tetrahedra. Oh my goodness.
But again, what's interesting is that you get them by joining the points,
Yeah.
Mhm.
and it just
And look at the dodecahedron with 5 tetrahedra creates a pentagonal dodecahedron.
mhm.
That is a pentagonal dodecahedron. Oh my gosh, the universe is so complicated.
Yeah, but if for me anyway, if this is falling into place, it's also so simple because everything manifests out beyond the basic tetrahedron.
Exactly right.
And then when you take on the duality, so you basically you start with 2 tetrahedron, and then as you say, the inside one gets pulled out,
Yeah.
and then if
Sure.
you have more than one, it gets pulled out. Join the points, you get a cube, you get a dodecahedron, you get a pentagonal one, and you can see the shapes of those very quickly.
Well, look at this beautiful dodecahedron.
Yeah.
It has 5 cubes. Dodecahedron with 5 cubes.
And the star thing.
Boy, I'll tell you, that blows my mind. Wow. So, coming back to fuller explanation, shall we just continue reading?
Sure.
Good. I think we skipped in order to get there, didn't we? No?
No,
No, we
no,
read
didn't.
all that.
We skipped one paragraph up the
We
top.
did? Duality.
Above duality, right below.
Oh, okay. Yeah, we may have skipped up there.
We have conspicuously ignored. Is this the one we
No,
not
I'll keep
read?
going.
We have conspicuously ignored one
No.
member of Plato's polyhedral family. What is the tetrahedron's dual? Following Loeb's example. We read this.
Yeah, I know. Keep going. I mean, it was up.
Okay, therefore, by interchanging the 2 elements to find the tetrahedron's dual, we generate another tetrahedron. This is 4-7b. Once again, the minimum system stands out. Only the tetrahedron is its own dual. Put 2 of them together to check. 4 windows, 4 corners line up, and curiously, the combined 8 vertices of 2 same-sized tetrahedron outline the corners of a cube, as Fuller is never tired of explaining. It just doesn't show a picture of it. You know, really, I mean, this right here, somebody ought to take a red line and just draw the cube around this thing, right? Okay. Here we go. Now we're going to start talking about truncation and stellation. Who wants to read?
I can read. I mean, it's no problem. Truncation and stellation. The introduction of 2 operations explored by Arthur Loeb will further elucidate the relationships between polyhedra. By altering and combining the 5 regular polyhedra, we can generate new shapes. One of the geometric phenomena that inspired Fuller's coinage, intra-transformabilities. Loeb's observations will help to clarify the meaning of this polysyllabic Fullerism. Truncation involves chopping off corners so that they are replaced by surfaces. Truncation of 3 valiant vertex will generate a triangle. Four vertices become squares, and so on. The number of edges determines the number of sides of the new polygon. Notice that the definition does not specify how much of the corner is sliced away in truncation. Loeb's work reinforces our emphasis thus far on topology, studying the numbers and elements of valiancy rather than size. The location of the slicing is therefore unimportant until the truncation planes move inward far enough to touch each other. At that point, the edges between the new planes disappear, and so the topology changes. Figure 4.8 shows various possibilities, including the final chop, the mid-edge point. The special limit case called by Loeb degenerate yields some interesting results, as we shall see. For example, degenerate truncation of a truncation unexpectedly turns out to be another member of the Platonic family, the octahedron as revealed.
And we're going to go look at that figure 8a. This is the truncation. And as they point out, it's a topological event. And so there's no dimension. And this shows a truncated tetrahedron until it reveals an octahedron.
Right.
An
Yeah, keep
octahedron,
slicing it down each corner. Wow. Yeah.
I never knew that a truncated tetrahedron is an octahedron, which reinforces the implication that this octahedron is part of the cube, is part of the tetrahedron. It kind of reinforces the fact that energy seems to manifest or re-demonstrate itself and reinforce itself until the universe looks like a cube and looks like an octahedron. Somehow. Boy, Ann, you have missed some heavy duty stuff.
Okay, I'll catch up. Okay.
Yeah.
Mm.
We had some really cool graphics about how what happens with duals, and then now we're starting on truncation
Mm.
and stellation. Those are the things we're going to be talking about. And we just measured a truncated. This is a tetrahedron. When you start chopping off its planes, it moves from this shape to this shape to this shape to that shape. I don't quite see how it gets to the octahedron, but that's what we just read. And we're going to continue reading. Is everybody ready to continue reading? We've only got about 10 more minutes of reading.
Sure.
Shall we continue?
Yeah, I don't know.
I think you may have to decide on when we are stopping as well, because I don't want to miss anything. For Christmas.
Okay.
Oh.
Let's see, what page is this? Because maybe we can. Yeah. Oh, Truncation. Yeah. If we finish this, we can posit a next thing, which is an experiment, which would be good for next week. So let's just finish these two paragraphs and then we'll pause. Who wants to read?
I could finish it. I mean,
Okay.
readers interested in learning more about these concepts and the mathematical analysis involved should read Space Structures by Arthur Loeb. Although we introduce only the vertex truncation, Loeb's studies extend edge truncation as well. For our purpose, of becoming familiar with the interconnectedness of basic polyhedra, we explore just one of Loeb's discoveries in the following pages. Then, when we see these shapes again in the context of the synergetics, some of their important relationships can be anticipated. Whereas truncation cuts off corners, stellation is accomplished by the addition of a corner imposing shallow pyramid on a formerly flat face. How many sides the pyramid will have is determined by the number of edges of the face to be stellated. Figure 4.9 compares the stellated cube and a stellated octahedron. Notice that as required by their different faces, the cube superimposed pyramids have 4 sides, while the octahedron has 3. Degenerate stellation occurs when the altitude height of the added pyramids is such that adjacent faces of neighboring pyramids become coplanar, as will
Coplanar.
yeah, as will be illustrated next.
Okay, so there is your stellated cube and octahedron. And maybe if we took 3 seconds here and go over
Sure.
to our Google. Go ahead.
No, I said, sure, go ahead, go ahead.
Stellated cube and octahedron. These aren't going to spin around. Here's a stellated octahedron. It looks like a double tetrahedron to me.
Yeah. No,
Well,
actually,
go ahead.
no, I actually can see it. I can actually see what you're talking about here.
There's a double tetrahedron. He's calling it a stellated octahedron. The stellated octahedron is the only stellation of the octahedron. It is also called the stella octangula, Latin for 8-pointed star. It looks like a double tetrahedron to me. Does it look like a double tetrahedron to you?
Yes.
Yeah, well,
Yeah.
that's what it does. It seems to me just a reverse process that we've been doing before.
Exactly.
Because now it's taking the
That's back in.
drop the edges of the cube
Yeah.
or the octahedron, and you end up seeing what's left, which is the double tetrahedron.
Yeah. Wow.
And if you got the double tetrahedron, I guess if you add the points, you should get we get a cube and not an octahedron.
Yeah. So a
But
stellated double tetrahedron is an octahedron. No, a stellated octahedron is equal to a double tetrahedron.
Right.
Wow.
Man, so these shapes seem to be redundant, and maybe that's why our 3D reality is so persistent, is because all of these shapes combine in such a way as to where these implications are constantly repeated. We're going to end off with an experiment here. We're going to end. Wow. Richard, how are you feeling? What are your takeaways so far today?
Well, I guess I'm feeling really invigorated with the fact that we've been going through this together, and equally frustrated that those formulas that we started out with aren't working quite the way that they see, the way they were being described. But we may have got through that in realizing that when we do the dualities and do what you originally said was add the vertexes and the faces together and then subtract 2, you should equal that other number. And when you did it, or when we did it together, that's exactly what it did. So in that sense, I guess we didn't read far enough into the chapter at the point that we were frustrating ourselves. And now that we have, it's starting to become clearer.
You know, may I interrupt you to say, if we then go back to that table, because you're pointing out something wonderful. I'm so glad you shared on takeaways first. I'm trying to get to that, my share here, and I want to share this table. Bam. There's where the gray areas were. And what you just said is that perhaps we didn't read properly. However, this duality seems to be reflected in those highlighted and the interchangeable 8s and the interchangeable 20s. That seems to be what you're saying, Richard. Is that what you're saying?
Yeah, it's in the, when you put them together and follow that constant 2, whether it's the polar 2 or the cell 2 or just 2, then everything works. So 4 plus 4 minus 2 equals 6. 8 plus 6 minus 2 equals 12. 8 plus 6 minus 2 equals 12. 20 plus 12 is 32, minus 2 is 30. And then 20 plus 12 minus 2 is 30. So it works all the way down.
Yeah.
Um,
Okay, good. And then that leaves us to start on page 57 next time around. So let me not interrupt you on your takeaways. Richard, do you want to summarize again and then hand it off?
no, I'm complete, thank you. Yeah. I'll hand it off to Joe. What's your takeaway, Joe? How are you feeling?
I'm feeling good. You know, it's something where, yeah, working through that was kind of forcing me to, you know, slow down and actually, you know, kind of go through the mathematics of it. And you know, that's something that's encouraging. That's a takeaway to a lesson, something I need to learn. And yeah, the explanations are, I think, you know, obviously I think Amy has thought this through, so it's just a matter of spending a little bit of time with the text. You know, I found also pretty interesting that last um part that we've talked about with the stellated octahedron was actually very interesting to me. And I just noticed that actually was something that was part of appears in and I put it in the chat, one of MC Escher's print. So I put, and that's extremely interesting to me because it's also something that's highlighted in uh, Gödel Escherbach. Not that print per se, but MC Escher, obviously.
Well, I'm going to show that, Joe, because to not show that would be a tragedy at this juncture, I think.
Yeah, it's
I'm
pretty.
going to try to find it's pretty mind-boggling. Here comes Escher with his
And he is an interesting artist to see the patterns that he's able to draw. It's pretty remarkable. And when you think about Dole, and you think of his hand, you know, his most famous drawings.
yeah, and here he's got an octahedron stuffed in the middle of a double tetrahedron. So here's your Merkaba. I think I'm seeing a Merkaba, and I'm seeing a tetrahedron jammed in the thing. So he is kind of like combined all these duals and
Exactly.
kind of to me reiterates or reinforces what I said about how the implications of these truncations and stellations are so standard to these basic solids that they continue to reinforce themselves. And I think that's what that is saying, if I may say so. Wow, Joe, thank you for sharing that.
Yeah, it was pretty cool. It was pretty cool.
I think
So
I'll put that. Oh, you already put that in there, didn't you?
yeah, yeah. So that was but yeah, so I mean, no, it's actually interesting and looking about this and even how to think about duals. So yeah, I mean, but so my takeaway is a lot of homework and as well as just spotting these patterns and starting to understand these patterns a little bit more. Anne, how do you feel? What do you take away from today?
I'm glad I could come back to the meeting and hear the end of it. And actually, Joe, I'm glad that you could join us today because your flu has been since Wednesday, right? It was pretty bad back then. So
Yeah.
that very happy that you're well enough to join us today. And just now, as you said that you got your takeaway is a lot of homework. So my takeaway is actually to read back on the things that I've missed prior to, because I think I missed about a week, and also to check in to see what it is, the explanation for that the numbers that didn't quite you know, add to the formula he gave. So I'm gonna look into that one. So very happy to actually it's amazing how he's described the double tetrahedron. Yeah, and I'm gonna find out more about what stellation is. And yeah, to the next meeting then. Yeah, Steve, how do you feel and what's your takeaway?
Well, my brains are blown out because I thought today was going to be a resolution of the relationship formula, the n squared minus n over 2, which I've come to love and appreciate and find great meaning in terms of being able to explain how complicated things can get. And I thought that this Euler's formula would simplify things, and it created those highlighted elements in the table, created some real dissonance for me. And then to have it all come around to somehow that dissonance relates to duality, and then the reoccurring implications of these basic solids just truncating themselves and dualing themselves just as mind-boggling. It looks to me like I thought, oh my gosh, I'm going to have 4 years of synergetics resolved tonight as I walked into this. And what I have is I haven't resolved anything, and I've got another 4 years of contemplation ahead of me to try and figure out what the heck this is all about. So I'm just grateful you were all here to go through this, because my brain quit several paragraphs ago, several pages ago. So I'm real honored and real thrilled. And I'm complete. And we have a few more minutes. Did you want to talk about a Christmas schedule, Anne? Is that what you were suggesting?
Yeah, so that I can make sure I don't miss anything. So definitely next week we are on, yes?
So what?
Next week. We still
Yeah,
have,
next week we would normally be on. That'd be the 14th. Christmas is like the 24th or 25th, right?
yes.
Yeah, so I mean, if I look at this calendar here, I'm looking at my calendar on my computer. The 25th is a Wednesday.
Right.
Do we want to take off for the holidays? In fact, as I recall, we usually quit around the 14th and then come back on January, but that's always frustrating to me. And if that's what everybody wants to do, that's what we'll do.
Yeah, whether people are traveling or not, I'm around. Yeah. Just that whether in I know Christmas in the US, people travel a bit to get back home and spend time with family. So it's up to you. Mm.
So Richard, what are your thoughts on taking a break for the holiday?
Well, just in terms of our own planning, which is not finalized yet, but it's quite possible that we could be traveling on the 21st. And then 21st, 28th, that would suggest to me that we do wrap it up on the 14th and come back in January.
Okay. How does everybody feel about that?
Yeah. Well, I'm okay if you all are traveling, then go celebrate your Christmas, have a great time. And so do you want to come back first week of January, which is on the 6th, I think, 5th or 6th, I think.
Yeah, the summary is we'll do next week, the 14th, and then we'll come back on the weekend of the 4th, 5th. It's the 4th, 5th, It's next week is the 14th, 15th, depending on your continent. And then our first comeback would be January 4th or 5th, depending on where continent you're on.
Right.
All right, that's our plan. So that sounds good?
Right, yeah, that
All
works.
right. And we'll meet next week and make sure that we're there. And I hope my brain doesn't explode between now and then.
Take care.
Back to Reed. Back to Emmy, yeah. Take care.
Thank you very much.
Take care.
Thank
Next
you all
week.
very much.
For Wednesday. Bye.
Enjoy the recording. Enjoy the recording, Anne. Whew. Prepare to deep breathe.
Okay.
All right. Bye-bye.